Imagine trying to find one specific piece of information hidden inside a chaotic cloud of floating data. To find what you're looking for, you'd have to grab and look at every single piece of paper until you finally got lucky. Now think about the mailroom in a modern apartment building. It's the exact opposite of that chaos. You have identical mailboxes lined up in a neat row, and they are all numbered sequentially, one after another. Because the boxes are organized by number, you don't have to guess where a letter goes. If you're looking for box 42, you can walk straight to it. You don't have to open boxes 1 through 41 just to find the right person. In programming, an array works the same way. It's a row of digital boxes in the computer's memory, all grouped under one single name. Instead of holding mail, each box holds a piece of data, like a test score or a name. Understanding this structure is a foundational skill. It's one of the first steps toward understanding how computers manage and retrieve large amounts of information efficiently. To use an array, there are 3 rules to keep in mind. First, elements. This is just the actual data you're storing. If you're tracking a class, your elements are the scores themselves, like an 85, a 92, and a 78. Second, indexes. This is our counting system. In programming, we almost always start at 0, not 1. So that very first score is at index 0, the second is at index 1, and it continues from there. Third, contiguous memory. In the computer's physical hardware, these boxes are literally touching. There are 0 gaps between them. This physical touching is why arrays are so fast. If the computer knows where index 0 is, it can do a quick bit of math to find index 500 instantly. It never has to search through the boxes in between. Grasping these under-the-hood mechanics is what helps you think like an engineer. You aren't just memorizing code. You're learning how the machine actually handles your data. If this breakdown is making sense so far, give the video a like and share it with your study group. Subscribing is the best way to keep up with these core concepts. To see why this structure matters so much, we have to look at the variable chaos programmers faced before the array was even invented. In the early 1950s, a single variable could only hold exactly one thing. To record the scores for a class of 100 students, you had to create 100 different individual variables by hand. The math was a nightmare. To find an average, you had to manually type out the math for every single variable. If one more student joined the class, you had to go back into your code and rewrite the entire equation. Before there was an organized way to set aside space for information, programmers managed dense manual wire routing on machines that filled entire rooms. In 1957, the programming language Fortran formalized the concept of the array. It gave scientists a way to handle massive lists of numbers without having to name and manage thousands of separate variables one by one. This wasn't just a shortcut, it was a structural necessity. It allowed computers to handle the complex, real-world math early hardware was built for. Putting data into a neat row led to one of the most powerful concepts in computer science, automation via the loop. Because an array uses sequential numbers, a loop can start at index 0, do some math, and step forward until it runs out of items. If you add more data, the loop automatically adjusts to process the new items without changing your code. We can see this history in early punch cards, which used organized columns of numbers to represent sequential data storage long before modern screens existed. Arrays allowed computers to process the massive, scalable data sets we rely on today, from global databases to modern graphics. Now that you know how a single row works, are you ready for 2D arrays?